We saw in the last section how to fill missing values in a data set and then convert it to numbers. Well, we filled it with pandas and then we converted it to numbers using scikit-learn. But it'd be nice to fill missing values with scikit-learn and convert it to numbers with scikit-learn. So we're kind of sticking to the one library. Let's see how we do that. So first things first, we'll need to reinstantiate our car sales missing data because we've kind of filled the missing values in place up here using pandas. So the one we have right now already has its missing values filled. So we'll reread it back in, read CSV, data. We're going to go car sales. I think I got a few missing. Extended. Where is it? Car sales missing data. Extended missing data.csv. Beautiful. That's what we want. And we'll just check. Why am I doing car missing? Car sales missing.head. Wonderful. Now we'll just clarify whether we have some missing data in this one again. How do we do that? Is na.sum. Wonderful. So we have some missing values. Not so wonderful if you're actually working on this data set because ideally your data set doesn't have missing values, but that's all right. We're going to figure out how to fill them up. So how do we do that? The first thing first, we're going to split it into a subset. Well, first we're going to get rid of the rows which don't have price values. And then we'll split it into X and Y because we don't want to deal with data that doesn't have labels. Car sales missing dot drop NA subset equals, we're going to give it the price column in place equals true. So what we're saying is basically with this line here, get the car sales missing data frame, drop the NaN values that are in the subset of the price column. These 50 values in the price column that don't have values, remove them from the data frame. And then we're going to recalculate how many missing values we have. I might put here a little comment, drop the rows with no labels. Beautiful. We've lost some from the make, color, odometer, and doors columns because they might have been overlapping with the samples in the price column that had missing values. So what's next? We want to split into X and Y. Plenty of practice doing this. This is what a lot of machine learning problems end up being, right? It's turning your data into features and labels and then getting a machine learning model to hopefully learn some patterns in those features and predict the labels. That's what we're going to try and do here. Axis equals 1, beautiful. Y, we've seen this before, car sales missing, price. So again, we're just using these 4 columns here to predict the price column. Well, that's our goal anyway. So how would we fill the missing data, take care of these missing values with scikit-learn? Well, let's see. We've got 2 little handy, well, one we've seen before, but one we haven't. Import simple imputer. What we might do is fill missing values with scikit-learn. Now, you might recall right up there when we started this part 2 of scikit-learn, or part 1, which is getting the data ready. Filling missing values is also called imputation, which is what this does. It's a simple imputer from scikit-learn. And that's going to help us fill missing values. And then we've seen this one before, which is the scikit-learn.compose import column transformer, which allows us to define some kind of transformer and then apply it to whichever columns that we want to use it on. We want to just do it the exact same we did it with pandas, but this time just reproduce it with scikit-learn. So fill categorical values with missing and numerical values with mean. There we go. I'm kind of writing these notes like so we can remind ourselves and communicate through our code, make sure we're kind of talking it through, doing the right steps, because otherwise you can get a bit lost with everything going on. So simple imputer, we're calling this class that we just imported here. We're going to tell it this strategy equals constant. So the strategy we want it to fill, so it's basically going, hey, run over the categorical values. I've shortened categorical to cat here. It's going to go over, it's saying for every value, keep your strategy constant, and the fill value is going to be missing. Okay, that's starting to make sense. And then we're going to have a special one for our door feature, simple imputer, because door is, again, that little funny one that is numerical but is also categorical. We're going to keep this as constant. And we're going to say fill value equals 4. Nice and simple. And then we'll have numerical imputer, which we could have really called num imputer. Actually, let's do that because we're keeping these fairly short. Num imputer, simple imputer, strategy equals mean. So we'll see what these mean in a second. We're just kind of, as I said, we're working through it. And we're going to go define columns. So cat columns or cat features equals make and color. And then we've got a door feature because, again, remember, doors is special case. And then we've also got num features, which is odometer. KM. Wonderful. And then what we're going to do is create an imputer. Something that fills missing data, because that's what imputation is, right? If you hear that term, imputation, kind of referring to find a missing value and fill it up with something, or calculate something to fill it with. So this is where we're going to leverage our column transformer. I love that word, column transformer. It always makes me think of Optimus Prime for some reason. What's your favorite transformer? Mine's definitely Optimus Prime or Bumblebee. On the hype train there. Getting distracted, Daniel. We're talking about machine learning. Well, actually, transformers are machines that can learn, so we're not really getting distracted. So what we're doing here is we're setting up our imputer and kind of passing it a few things to get it ready. So just bear with me a second. I'm kind of coding and trying to talk at the same time and getting distracted. So door imputer, we're going to go door imputer, and then we're going to go door feature. And then finally, one more, and we got num imputer, and then we're going to go num imputer, and then we're going to go num features. Beautiful. Whew. We've got a fair bit of code here. And then we're going to go transform, one more, transform the data. So we're going to go filled x, because remember, x has some missing values at the moment. If we go up here, we want to go x.isNA.sum, which is just the same as up here, except we've got no price category there. So we come down here, filled x equals, we're going to take our little imputer here, imputer.fit transform x. And then we're going to have a look at filled x. Will this work? Fingers crossed. We've got a lot of code here. We've got 24 lines of code, plus comments. It worked. No errors. What has actually just happened? Well, let's step through this. What we might do is zoom out so we can, just a little bit so we can see it all in one hit. Beautiful. So what we've done is we've imported from scikit-learn simple imputer class as well as the column transformer class. And then we've defined some imputers. And remember, imputers are just filling missing data using the simple imputer class, which takes strategy and a fill value. If the strategy is constant, we have to pass it a fill value saying, hey, go to the categorical columns, constantly fill them. If you find a missing value, just fill them with missing, the string missing. The same thing for our door imputer. It's going to say, keep the strategy constant. So for every missing cell, do the same thing and fill it with 4. Yep, that makes sense. And for our numerical columns, in this case, which is the odometer column, fill it with the mean. So keeping that one nice and simple. Then we've defined which columns are which. So our categorical columns are make and color. Realistically, doors is also that, but we've kind of made it its own because it's, again, halfway between a number, halfway between a category. So we've got the door feature, and then we've defined the numbers feature, or the numerical features, which is our odometer. And then we've used the column transformer class, which is what we imported, and we created an imputer, passing it the imputations we wanted to do, or the transformations we wanted to do. So these are the names. So that's what column transformer takes. It takes a list of multiple different transformers. So see here, we've got a list. And now within the list, we have tuples of the name, the imputer we want to use. This is just the name of the imputer, right? So if we had to access this imputation later, we can use this as its name. I've just kept it simple and called it the exact same thing as what the variable imputer is. And these are the features that we want this specific imputer to change. So this one, cat imputer, is going to use cat imputer on the categorical features, door imputer on the door feature, and the numerical imputer on the numerical features. Whew, that was a mouthful. And then once our transformer is defined, we can, I've called this filled X because we're going to use our imputer and fit transform on our X data to fill up the values of X. Wow, but don't take my word for it. Let's see it in code. So car sales filled, let's create another data frame because we want to use the same checking method that we've used before. We'll pass it filled X, and then we'll pass it the column names. This is just the names of what these respective columns were. You can see car is the make, color, doors, and then odometer. So that's all we're going to do here. Make, color, doors, odometer, pass it KM as well. And beautiful, that should work. Now we're going to have a look at the head of this data frame here, car sales filled, dot head. Wonderful, that looks familiar to what we've seen before, but the icing on the cake here, the real test is seeing, is NA, what does this output? Beautiful! We now have no missing values, thanks to this bunch of code that we've written here. So we've used simple imputer plus column transformer to fill the missing values, so these missing values here, with some preset defined ones that we've created here. And now, car sales filled, which is what we've made out of our transformed data, now has no missing values. Beautiful. So now what should we be able to do? We have no missing values, should be able to convert these into numbers. So when we come up here, we have some code that has done this before. This is it. So we're going to copy this, come back down. This is the only time I'll let you copy and paste code. I know I've said that before, but again, to just save us a little bit of time, what we might do is again, split car sales filled into X and Y. So we want X equals car sales filled dot drop. Oh no, that already is our X value. Beautiful. So we can move this into here. Car sales filled. Wonderful. So this is telling us we've got a sparse matrix here. Now, what can we do? Now, we've got our data as numbers and filled. No missing values. Let's fit a model. I'll put that here. Let's fit a model. mp.random, just to make sure everything's working right. Always trust the code. Always trust the code. That's what we're going to do. We're going to re-import model. We've seen this up before. So random forest regressor. We're going to have heaps of practice doing this from sklearn model selection. We want something to split our data into train and test. And then we also actually want to split our data into train and test by going x train, x test, y train, y test equals train test split. Wonderful. And we're going to pass it this time transformed x. See this variable here? Because what we've done is we've passed it car sales filled and basically just turned all the categorical features. We've one hot encoded them. So we'll go here, transformed x. We'll also pass it y because y is still saved in memory. Y doesn't have to change because that's just labels. They're already numbers. And the test size is 0.2. Wonderful. And so we'll set up our model, which is a random forest regressor. And then we're going to model.fit. So this is telling our model to find, hey, random forest regressor, find the patterns between x train and y train. And then we're going to model.score on our test data sets. This is going to say, hey, evaluate, I know you've found some patterns in this training data set, but now evaluate those patterns on this test data set. And moment of truth, shift enter, Beautiful. We're getting a warning here because there's some changes happening in a future version of Scikit-learn. You might not have this warning if you're using Scikit-learn version 0.22. All it's saying is that n estimators will be changed from the default 10 in version 0.2 to 100. So we can basically get rid of this warning by going here equals 100. Wonderful. So even though this model has more estimators than the previous one we've used on our car sales missing data, it performs worse. So this one gets a score of 0.219. And if we come up here, where is it? We did train a model in the previous section. This has got 3.304. If the maximum score is 1, they're both not doing as ideally as we might like, but why do you think this one performed worse? Well, it's because it's only got 950 samples. So if we go len car sales filled, as well as len car sales missing, oh, no, we want maybe the original car sales. There we go. So our previous model was built on this one, and the model we've just built was built on this one. So one has 1,000 samples and the other only has 950 samples, which is why it's done slightly worse. And so that's a big paradigm of machine learning, right? Like most of the time, if you have more data, usually a machine learning model is able to find better patterns. And so that's kind of what's happened here, is that because we've dropped the samples that don't have labels, our model hasn't been able to find as many patterns, even though we only removed 50 out of 1,000 samples. We have covered a lot here already so far. But the most important key takeaways from this are most datasets you come across won't be in a form ready and immediately to start using with machine learning models, and some take a bit more preparation than others. And so most of the time what you'll have to be doing is your data will have to be numerical and it can't have missing values. And so the process of filling missing values is called imputation. And the process of turning your non-numerical values into numerical values is referred to as feature engineering or feature encoding. So, with that being said, we've covered part 1 of how to deal with your data. Let's get into part 2 and figure out where the hell did I get this idea for choosing a random forest regressor for our problem? Why did I pick this machine learning model? You'll have to wait and see.